here that affects what happens over here, but in a way that doesn't involve sending a signal from one to the other at the speed of light. Right? If you wanted to think of it in terms of signaling, you'd have to be sending your signal at speeds much, much greater than the speed of light. And that seems wrong. So physicists call this non-locality. Right? So it's violating the principle that something that happens here should only be able to affect things in its immediate local neighborhood until some time has passed. It's a really weird idea, and this is another thing. In the same time Schrödinger was doing his cat thought experiment, Einstein wrote a paper with two young colleagues where he introduced this idea of entanglement and said, this is an indication that quantum mechanics has to be incomplete. And nobody really knew what to do with that for about 30 years, but a guy named John Bell in the 60s showed that there was actually an experiment you can do that will distinguish between the quantum prediction that things are not local and weird, and the sort of theory that Einstein preferred. And people have done those experiments starting in the 1970s and continue to do them today. And every time anybody's done those experiments, it shows that the weird thing is true. That these things are really correlated in a way that does not respect the speed of light limit between the two. Lots of ways to think about how that happens, right? And one of the ways of reconciling that is to say that, well, all we really deal with is information, so it doesn't make any sense to talk about an underlying reality. And that's an approach that some people take. That's the sort of philosophical thing about Einstein so much, but it really is a real phenomenon. Some of the people have to work very hard to understand. There's a theory, a way of doing quantum mechanics is called Bohmian mechanics, or de Broglie-Bohm theory that does that sort of thing. It says that particles have definite positions and momenta at all times, but that they're pushed around by this guiding field that is sort of an extra wave that travels through the universe at speed, but that's a non-local thing. It changes faster than the speed of light. And that is an internally consistent way of doing quantum mechanics. It's kind of weird, but all of the ways that people come up with doing quantum mechanics are kind of weird. So that's a thing you could do. So, other questions? Science fiction recommendations recently. People ask me this and then I go completely blank. Recent science, there's an astronomy book that I've been working my way through that's on a textbooky side of things, but by Ethan Siegel, does a blog called Starts with a Bang, and it is like Beyond the Milky Way or something like that. But it's by Ethan Siegel, Starts with a Bang. That's a really nice survey of astronomy with absolutely no math, which is the best way to do astronomy. So last question in the back. So there are ways. So you're asking about a thing called the measurement problem, or the sometimes observer effect, right? The notion that is implicit in the video that I started this with, where you open the box and that makes the cat inside pick either alive or dead, and so that the act of observing something changes its reality. That is one of the ways that people come up with to deal with the weird stuff, right? So the thing that's weird is not that you don't know what the state of the cat is while it's inside the box, because that sort of thing happens all the time, right? What's weird is the notion that when you open the box, you force it to pick one or the other, because we know that we only ever see live cats or dead cats. We don't see half-alive cats, right? So one way of dealing with that is saying, well, the act of seeing it causes it to change, to pick just one or the other. And that's a whole class of theories that people do. There's another way of doing it, which is to say, which is many worlds, which is the cat is both alive and dead, and then when you open the box, the cat continues to be both alive and dead, but now you are in a superposition of knowing that the cat is alive and knowing that the cat is dead. And and the universe continues on with everything in a big superposition. And that also works perfectly well as a way of interpreting things. And so both of those, like I said earlier, both of those give you exactly the same predictions for measurements you can actually make. So it's sort of an aesthetic choice at some level, which way you prefer to think about the universe working. At least until somebody comes up with a way to distinguish. I mentioned John Bell a little while ago talking about entanglement. There was this problem of, is this entanglement thing real? For like 30 years, nobody knew what to do with it. And he sat down and thought really clearly and rigorously and analytically about what exactly does it mean for these two types of theories to be true, and then can we find a place where they predict different things? And so, and that worked brilliantly, and you can do an experiment that tests entanglement and show that it's really a thing. It's still an open question whether there's an experiment you can do that tests whether observing something causes a physical change that makes it pick one state or the other, or whether the universe remains in an ever-expanding superposition. Somebody may come up with it someday, nobody has yet. So. Absolutely. And the results that you predict work to 15 decimal places. So works spectacularly well. It's just how do you interpret what's going on inside the box. And that's kind of, at this point, is still essentially an aesthetic choice. You pick whichever one you like better. So I think we're out of time. I'm happy to answer questions down here. We'll have one question. So thank you all for coming out. It's fun.
Today, it is a great pleasure to introduce today's speaker, for a number of years Birmingham, and never decided to invite him. It's really a great pleasure for me to be here. He did his undergraduate studies at the Institute of Technology in Eindhoven. He got his doctorate from the University of Amsterdam in 1986 or so. He was then a postdoc at the State University of New York in Stony Brook before he was lured to Fermilab by a Russian publisher. He stayed at Fermilab for several years, and in 2010 moved to Argonne National Lab. During his career, in his doctorate, he worked on TAM-SM production and decay, and in p-Barr-Peak physics and the D0 experiment, maybe most of you know, but maybe not, the kind of rite of passage for a hadron collider experiment is to do a good job of measuring the mass of the W boson, trying to do precision physics in a very high energy collider, and Marcel was instrumental in the first measurement that D0 made of that quantity in the early 90s. He then took on another thankless task as one of the leaders of the silicon detector project, the upgrade of D0. That was a device with 800,000 channels, and there is many problems on the way to completion, but completion was achieved, and in fact it ran right through to the end of the collider running at Birmingham. So some rather impressive achievements in his career, but now he's paying for it. He's a member of the Bell-True Program Advisory Committee. He's a member of the Large Hadron Collider Committee at CERN. He, for our benefit, is a member of the Electron Ion Collider Detector Advisory Committee at Brookhaven. And then to complete all this, he's got the pleasure of being a member of the Particle Physics Project Prioritization Panel, which is trying to give a shape to particle physics in this country this year. So it's with great pleasure. Please join me in welcoming Marcel Dugastel.
Sorry, well, thank you, Mark, for this nice introduction. I don't think that measuring the W mass is still a rite of passage for everyone. Anyway, so again, thank you very much for having me here. It's a great pleasure to be here. And this talk is maybe not going to be as much physics as you may want, but maybe more of the direction in which physics is going in a particular part of physics. So what I would like to talk about is the techniques and technologies of energy physics and the connections of these technologies. And to give you a little bit of the background, this actually came about very tangentially to the process that particle physics community is going through with in the sense that Jim Siegrist, who is director of the Office of Scientific Physics and Science, would like to understand better, what the relation is of high-energy physics to other science disciplines and society in general, and that's why this came about.